Hello everyone, welcome to Agentic RAG from Scratch series. In this series, we are building a production grade Agentic RAG system from scratch. This is episode 5. In this episode, we'll take a deep dive into LangGraph library and understand how to build a powerful agent workflows from ground up. We will begin with core fundamentals covering concepts like state management, how states are updated, reducer functions, input and output schemas, and how to work with messages effectively. Next, we'll explore how to pass context between nodes, enabling more intelligent and dynamic agent behavior. From there, we'll move into connecting nodes using edges and dive into different control flow patterns such as sequence, parallel execution, conditional branching, and loops. Once you are comfortable with these building blocks, we'll level up into advanced concepts like threads, checkpointers, memory stores, interrupts, and subgraphs. Once again, welcome to Building SaaS channel. Let's get started. Let's start by building a simple graph using LangGraph. Step 1. Imports. First, we import the building blocks from LangChain and Python typings module. We bring in any message, human message, AI message, and system message. These represent different type of chat messages in our system. Think of them as labeled envelopes, one for human, one for AI, and so on. We also import list and type dictionary from Python's typings module. We'll need these to define our graph state. Step 2, let's create a state. Now we define agent state. This is the memory of our graph. It's a typed dictionary with two fields. Messages, a list that holds the entire conversation history. LLM count, an integer to track how many times the LLM has been called. Think of this as a clipboard that gets passed between every node in the graph. Next, let's create a node. A node is just a function that does some work. Here, node A takes the current state as an input and returns an AI message saying hello from node A LLM. Every node receives the state, does its job, and returns an update to the state. Now we initialize the graph using StateGraph and pass in our agent state schema. This tells LangGraph every node in this graph will read and write data in this shape. It's the foundation everything else is built on. With the graph initialized, we register our nodes using add node. We give it a name node A and point it to our function. Right now it's registered but not connected to anything. That's next. Edges define the flow of our graph, the path execution take. We add two edges. Start to node A, so when a graph begins, it goes to node A first. Node A to end. After node A finishes, the graph is done. This gives us the simplest possible graph, a straight line from start to finish. Now we compile the workflow. This locks in our nodes and edges and produce a runnable graph object. Think of this like hitting build. Before this, we are just writing a blueprint. After this, we have an actual engine. Before we run it, let's see what we have built. Using Draw Mermaid PNG, LangGraph renders a visual diagram of our graph, showing the start node, node A, and end node connected by arrows. This is super useful for debugging as your graph gets more complex. Finally, we run the graph by calling invoke and passing in a human message, hello from user. The graph starts, passes the state to node A, and node A returns an AI message and the graph ends. Then we loop through all the messages and call prettyprint, which gives us a clean readable output of our conversation. Now let's dive deeper into state management in LangGraph. So here is something important to understand about LangGraph state. By default, when node returns data, it completely overrides the existing state key. Let's see what that looks like in practice. We have two nodes, node A and node B. Both returns a messages key. We chain them, start to node A, node B, and end. Now watch what happens when we invoke this graph with a human message. You would expect to see three messages. Human message, node A's reply, node B's reply. But what you actually get is only node B's message. Why? Because without a reducer, each node just overrides the previous state. Node B's return completely replaced by node A's output. This is the default reducer behavior. Last write wins. To fix this, we use reducers. A reducer tells LangGraph how to merge a new value into the existing state, instead of just replacing it. We import add from Python's operator module, and we use annotated from typings to attach it to our messages field. The add reducer simply appends new messages to existing list instead of replacing it. Now when we invoke the same graph, we get all the three messages: human message, node A, AI message, node B's AI message, printed cleanly one after another. Each key in your state can have its own reducer. If you don't specify one, it defaults to override behavior we saw before. Now the add reducer is great, but it has a limitation. It always appends even if the same message already exists. LangGraph gives us a smarter built-in reducer called add messages. Here is how it works. If a message with the same ID already exists in the list, it updates it in place. If it's a new message, it appends it. In our example, both node A and node B return a message with ID 1. So instead of two separate messages, node B's message replaces node A because they share the same ID. This is exactly what you want when you're building chat agents, where you might want to edit or update an earlier message rather than duplicate it. Now let's look at context. Sometimes you need to pass dynamic information at runtime, like the current user's name, their preferences, or session tokens. That's what context is for. We define a user context, then we pass this schema into the StateGraph constructor using context schema property. In our node, we add a second parameter, runtime. This gives the node access to whatever context we pass at the invoke time. And when we invoke the graph, we pass the context like this. The output says hello from node for user Rob. The node dynamically used the runtime value. Think of context as read-only config that flows through the entire graph at runtime without being part of state itself. Now that we know how to update the state and pass context, let's look at control flows. LangGraph supports 4 types of control flow. Let's walk through each one of them. Sequence. The simplest pattern. Steps execute one after another in a straight line. LangGraph gives us a shortcut method, add sequence. Just pass a list of functions and it automatically chains them together. In this example, we are chaining step 1, step 2, step 3, step 4, clean and linear. Use this when each step depends on the output of the previous one, like a pipeline. Control flow type 2, parallel. What if some steps are independent of each other and can run at the same time? Here, step 1 fans out to both step 2 and step 3 simultaneously. Then the both of them converge into step 4. We achieve this by simply adding multiple edges from the same source node. LangGraph handles fan out and fan in automatically. Great for tasks like parallel tool calls or simultaneous API requests. Control flow 3, conditional branching. What if you want a graph to make decisions and take different paths based on the state or context? We define a router function that returns the name of the next node. Then instead of add edge, we use add conditional edges. LangGraph calls the router function after step 1 and routes to whichever node the function returns. Since the user is Rob, the graph goes to step 2, change the name and it goes to step 3. This is the foundation of intelligent agent decision making. Graph adapts its path based on real data. Control flow 4, control loops. The most powerful pattern, loops. This is what makes agents truly agentic. We build a graph where step 2 loops back to step 1, creating a cycle. But cycle needs a way to stop, otherwise they run forever. We add a route function that checks the state. If there are more than 5 messages, the graph stops, otherwise it loops again. We also have a safety net, the recursion limit. If you pass config recursion limit 3 when invoking, LangGraph raises graph recursion error after 3 steps. We catch it gracefully with try expect block. Always use both a conditional exit in your logic and a recursion limit as a failsafe. This pattern is backbone for React agents and self-correcting workflows. So let's recap. Default reducers override state, use add to append, and add messages to smartly update or append. Context lets you inject runtime config like user info without populating your state. And the 4 control loops, sequence, parallel, conditional branching, and loops, give you full control over how your agent thinks and acts. So far we have built graphs, managed state, and control flow. But here is a question. What happens to your graph state after it finishes running? By default, it's gone. Every invoke starts fresh. We are fixing that with persistence. one of the most important features for building real-world AI agents. Checkpoints, threads, memory store are the three core concepts for adding persistence to our agents. LangGraph has built-in persistence layer that saves your graph state as checkpoints at every single step of execution. Think of it like a save file in a video game. After every move, the game automatically saves. If something goes wrong or you want to go back, you can restore from any point. These checkpoints are organized into threads, and together threads and checkpoints are the two core concepts here. Let's understand each one of them. A thread is basically a unique session ID for a conversation or a workflow run. Every time you invoke your graph with persistence enabled, you assign it a thread ID. All the checkpoints from that run get saved under that ID. You can pass it through the config like this. Think of threads as a conversational thread. Thread 1 is user 1's session, thread 2 is user 2's session. They are completely isolated from each other. A checkpoint is a snapshot of the graph state at a specific point in time, specifically after every super step. So for a two-step graph with human message input, we get exactly 4 checkpoints. Empty checkpoint, user input saved checkpoint, after step 1 checkpoint, after step 2 checkpoint. Every single step is captured. Now let's set up the checkpointer. To enable persistence, we import in-memory saver from LangGraph checkpoint module. Then when we compile the graph, we pass it in. That's it. Now every invoke automatically saves checkpoints. Then we invoke with our config passing thread ID. In-memory saver is only for development and experimentation. For production, we use LangGraph checkpoint Postgres library with real Postgres database. We'll cover that separately. Now that the state is being saved, we can read it back in 3 useful ways. To get the current state of the thread, meaning the most recent checkpoint, we call getState with the thread ID. This returns a state snapshot object, which contains the full state, the next node to be executed, and the metadata about when it was saved. Want to go back to a specific point in time? Just add the checkpoint ID to your config. Each checkpoint has a unique UUID that gets generated automatically. You can use this to replay, debug, or branch from any earlier state. This is incredibly powerful for debugging agents. You can literally rewind before a bad decision was made. And if you want to see every checkpoint that was ever saved for the thread, use getStateHistory. This returns all the 4 snapshots we talked about earlier, from empty start all the way to the final output. Think of this as a full audit trail of your agent's execution. Now let's look at memory store. The problem with checkpoints alone is they are scoped to a single thread. Thread 1 knows nothing about thread 2. So if the same user starts a new conversation, the agent has no memory of who they are or what they prefer. For real AI assistants, that's a problem. You want the agent to remember things about user across the sessions. That's where the memory stores come in. Now let's set up the memory store. We import and set up in-memory store. Then we compile the graph with both checkpointer and the store. The store is completely separate from the state. It lives outside the threads and persists across all of them. Memories in store are organized by namespaces, a tuple that acts like a folder path. So all the memories for user 1 go into 1, memories namespace. You can structure this however it makes sense for your application, by user, by topic, by session, or anything. To save a memory, we use store.put with namespace, unique memory ID, and the data. We generate a fresh UUID for each memory so they don't overwrite each other. The data itself is a plain dictionary. Store whatever you want. Here is where it gets really powerful. Inside a node, we can access the store through runtime object. We search the namespace with the user's latest message as query, pull back up to 3 results, and inject that info into the response. The output will include I like pizza, pulled from store across the threads personalized to that specific user. Store supports semantic search, not just keyword matching. If you configure the store with an embedding model, it can find memories based on meaning. So a query like what food do I enjoy would still surface the pizza preference even though the word don't exactly match. This is how you build agents that truly know their users, not just remember exact phrases but understand the context. Now that we know how checkpoints, threads, and memory work, let's dive into another concept that uses all of these concepts: interrupts. The feature that lets you pause your graph mid-execution, wait for human to make a decision, and then resume exactly where it left off. This is the foundation of human-in-the-loop AI, where an agent doesn't just run on autopilot but checks with the real person before taking a critical action. Imagine your AI agent is about to send an email, execute a trade, or delete a file. You probably don't want to do it without asking first. That's exactly what interrupt solves. When your graph hits an interrupt call, graph execution is suspended. Everything stops right there. State is saved using checkpointer. A value is surfaced to the user who is calling the graph. The graph waits indefinitely. When you resume with the response, that response becomes the return value of the interrupt call and the execution continues. The key thing to understand here, this only works because of persistence. The graph can pause and wait because the checkpointer has saved every bit of the state. Without a checkpointer, interrupts simply don't work. Before we jump into full example, let's quickly cover the command object, because it shows up when we resume an interrupt. Command is a special return type that lets a node do two things at once: update the state like normal node return and control the flow, decide which node to go to next. Normally, state updates happen in nodes and routing happens in edges. They are separate. Command collapses both into one, giving you a fine-grained control from inside the node. We'll use command specifically to resume value to wake up the paused graph. Here, we have an agent that generates an email and then asks a human to approve it before sending. This is a classic human-in-the-loop pattern. Our state has three fields: the conversation history, messages, email content, the generated email draft, approved, the human yes or no decision. The first node generates the email. In a real agent, this would call an LLM. Here we keep it simple. Nothing special here. It writes a draft into the state and passes control to the next node. This is where the magic happens. We call interrupt with the message, "Do you approve sending this email?" And that message gets surfaced to whoever invoked the graph. Execution stops right here. The function literally pauses at this line. The return value of the interrupt whenever a human sends back gets stored in approved and returned back into the state when we resume. The final node checks the approved flag and acts accordingly. If approved, email goes out. If not, it's cancelled. We wire up the sequence and compile with checkpointer. This is non-negotiable for the interrupts. So the graph looks like this. It starts and goes to generate email content, then goes to approve node, then send email node, and end. We invoke normally with the thread ID. Here's what happens. Generate email content runs and saves the draft. Approve starts running and hits interrupt. Graph pauses and returns an interrupt object to the caller with message, "Do you approve sending this email?" Send email has not yet run. The graph is now frozen in time, waiting. And because the checkpointer, it will wait as long as it needs, seconds, minutes, or days. Now, when the human says yes, we resume by invoking the graph again on the same thread with a command resume true. LangGraph loads the saved checkpoints, jumps back into the approved node right where it paused, and the interrupt call now returns true. The true gets written into state variable approved and runs send email, printing email sent. If the human says no, the same pattern but with false. This time interrupt returns false, state approved gets updated with false, and send email prints email sending not approved. The same thread ID is critical here. That's how LangGraph knows which paused graph to resume. Let's look at the last topic for this video, subgraphs. Subgraph lets you nest one graph inside another, like building with Lego bricks. Each piece is its own complete graph, and you snap them together to build something much bigger. As your agent system grows, you will run into three situations where subgraphs become essential. First, multi-agent systems. You have multiple specialized agents, one that searches the web, one that writes code, one that reviews it, and you will need them to work together in one pipeline. Second, reusability. You have built a great email approval workflow or a document summarizer. Instead of rewriting it every time, you package it as a subgraph and drop it into any parent graph that needs it. Third, team distribution. Different engineers own different subgraphs. They develop and test them independently, then compose them together, just like microservices but for agents. Now, There are two ways to connect subgraphs to parent graphs. The method you choose depends on one thing. Do the parent and subgraph share the same state schema or not? Different state schema, call the subgraph inside the node. You'll manually handle the translation between states. Same state keys, add the subgraph directly as node. LangGraph handles the wiring automatically. Let's see both in code. First, we'll build the subgraph completely independently. It has its own state, its own nodes, its own edges. It knows nothing about the parent. The subgraph has one field bar. Its only node prepends hi to whatever bar contains. Compiled and ready to go. The parent graph has completely different state. It uses foo, not bar. These two schemas don't share any keys. So to use subgraph, we wrap the call inside a regular node and handle the translation manually. Now the second method. When the parent and subgraph share the state keys, instead of wrapping the subgraph in a function, you pass the compiled subgraph directly as a node. That's it. No wrapper function, no manual translation. LangGraph sees the node 1 is a compiled graph and handles the communication automatically. Shared keys flow in and out seamlessly. Use this when you are composing graphs that speak the same language. That's it for this episode. We have understood state management, control flows, persistence, interrupts, and subgraphs. In the next episode, we'll be using these concepts and updating our existing chatbot application. If you want to follow along and try this out yourself, I have linked the full code repository in the description. Do subscribe to Building SaaS channel and turn on the notification so that you don't miss the next video. Thanks for watching. I'll see you in the next one.